Right, we have EE222. We will be continuing with our studies of milli machine, more machine, and soon after that we would start off with a problem on, we want to start off with a problem on sequence detectors. All right, so let's just quickly switch over to the document camera. Right, and guys, you would have been doing your project. If you haven't started yet, it is very important that you start. Do not leave it till next week. It's actually like a 2-week project. It's more like a 2-lab sort of project. And the 3rd lab you leave for spare, just in case you want to check something or help your friend. So I've given you 3 labs to do it. So it's equivalent of 3 labs. So in one lab, a few students, I was impressed, they were in last week's lab, week 11, they were able to finish problem number 1. This week's lab, you should be doing problem number 2. And if you are worried about, oh, we haven't done that particular topic yet, it's on the Moodle shell. You'll see my very own videos on YouTube, right? You'll see the link to them. Anyway, so we will do a problem today, not to worry. Last week we were looking at firstly the definition of finite state machines, right? Finite state machines. Then we said there are 2 types of finite state machines, either a Moore machine or a milli machine. So the Moore machine, let's have a quick review. A Moore machine, the output is a function of the present state only, right? And what example did we use? Have a look at this, question 2, right? So only the present state gives the output. A milli machine is a machine where the output, where the present state and the system input together, they form the output, all right? So that's known as a milli machine. So it's important that you understand this. Now I want to give you one more important point. And that is, all right, so this here was, we were talking about a Moore machine. Okay, this is a Moore machine. Now a Moore machine state diagram. Let us show you what is a Moore machine state diagram. A Moore machine state diagram. By the way, I think I should put down today's date. What is today's date, guys? It's, does anyone have today's date? 14th June 2022, and this is week 12, lecture 1. All right. Now, what does a Moore machine state diagram look like? Now, in a Moore machine, the state diagram is drawn slightly differently, right? Slightly differently. Let me give you an example, right? Let's say it's a 4-state system, right? You have 0, 0, 0, 1, 1, 0, 1, 1. And let us say, I'm just doing a random state diagram, all right? And let's say there is a loop going in that way, there is a loop going in this way, a loop going in this way, and a loop going in this way. Now, the only difference in the drawing of the state diagram is this. Remember, in a normal milli machine, this is a Moore machine, okay? This is a Moore machine state diagram. So in a normal machine, let's have a look at backwards. Let's have a look at this guy over here, right? Look at this particular state diagram. This diagram is a milli state diagram, right? Wait, maybe even better. There was no state output over there. I want to show you a system where there's a state output. All right, here, look at this one. Can you see there's input slash output? Input slash output. So the only difference over here is we have our inputs 0, 1, 0, 0, 1, 0, 1, 1. So I'm just making this state diagram up. All right? This is just an example state diagram. Now in a milli machine, your output would be what? This is what does this indicate? This number. That number indicates input. Then if you want to put an output, what do? You put a slash and then the output. Right? Slash output. Right? In a more machine state diagram, you put this. Okay? Okay, let's make that a 1. That is the only difference. That is the only subtle difference. Right? That is the only subtle difference. Okay? Let's now, so if everyone can see that, in our normal state diagram, the one which we've been doing till now, those are state diagrams of milli machines. We were actually, even if it was a more machine, we were drawing it like milli machine. But in fact, if you look at the two problems which we did, because I chose these problems in that particular way, this is a milli machine, right? That's a milli machine, so there'll be an input and output. In the more machine, there was no system output. Do you notice? There was no exact system output. The system output was the states itself. So that's why when we did question 2, where did we do question 2? I think we did question 2. We did this question 2 last week. It doesn't really make a difference, all right? Now, because there was no system output anyway, right? So sometimes there is no system output. When there is a system output, you have to determine between milli machine and more machine. Generally, if there's no system output, that becomes a more machine. All right, now let's look at a milli machine. Milli state machine. In fact, this is a replication of what I mentioned earlier on. So milli state machine, a milli state machine is where the output is the function of the present state as well as the input. Right? So let me show you what it refers to, guys. Let me show you what it refers to. As I've mentioned, look at this here. Look at this question. It's good that we have our own examples already. If you look at this question, which everyone has done, we've done both of them already, by the way. That output, the system output, is constructed using the current state, and if you look at it, the system input is involved. So if you look at the algebraic equation of the system output, you see the system input is involved. Yeah? The algebraic output, the system input is involved. X is there. X is the system input. All right? Now over here, in fact, there is no system output. But even if we were to, let's say, make an OR gate or make an AND gate or put a number of gates over here, but the only inputs into those gates are A and B, because this X is not involved, that becomes a more machine. So basically it's like this. If the system input is involved in the output, that's a milli machine. If the system input is not involved, that's a more machine. All right? Okay, so let me just draw a quick diagram. Let me just draw a quick diagram. Similar diagram to what we drew last week, but slightly different. Okay, so this is memory. This here is your clock line. In fact, in terms of theory, this is the only theory which you will see I usually ask. Is the machine a mini machine or a Moore machine? Output combinational logic, and then we say that's our output Y. Sometimes we call it Y. This here is our input. Sometimes we call it X, but doesn't have to be called X. This is next state combinational logic, and then of course there's always feedback going in. So if you look at it, the input X, have a look at it, that input X flows directly into the output logic, combinational logic. Now, another important point, guys, another important point. In mini machine, or milli circuit, the number of states are less as compared to more. The number of states is less as compared to more. Okay, why? Why? Right? In mini machine, okay, and the other point I want to say, state diagram for milli, the example is, I won't redraw. This one. That's a milli state diagram. Another one, let me show you another one. Okay, over here, notice output was not declared. Can you see? Output was not declared. So naturally that becomes a Moore machine. Right? Okay? This one. So I'll write down week 10, lecture 2. Right? Week 10, lecture 2, and the other one was, where do you go? This guy. No. This one. Which one is this? Can you tell me? Week 11, lecture 1. Week 10, lecture 2, week 11, lecture 1. Right? These are some examples. So rather than me drawing and wasting our time. Right? So that's it, guys. That's the only difference. Now, the question, this second statement. The number of states are less as compared to Moore machine. Why? Well, in a Moore machine, the output has to be declared in the state itself. The output has to be declared within the state. So the state is giving you 3 pieces of information. Number 1, the state gives you the state of the two, like let's say this one here, it's giving you the state of the 2 flip-flops. So 0, 0 means flip-flop A is 0, flip-flop B is 0. 0, okay, this one here. 1, 0 means flip-flop A is 1, flip-flop B is 0, depending on what you number, one to number it. Okay. And it's also giving you another piece of information. When we draw this state diagram, it's giving you the value of the output. So in order to accommodate some possible outputs, you may have to add an extra state. So let's say if you needed an extra state, let's say there's 0, 1, and output 1, and another one with 0, 1, output 0. So you have to have two bubbles to accommodate that. Right? Okay? Because remember, you are showing 3 pieces of information. And in the mini machine, it was very easy. In fact, the easiest scenario is when there is no output. No output, nothing to worry about. Yeah? The easiest scenario is that was the easiest scenario when there was no output. In this particular case, our output is shown along the transition lines. Can you see those transition lines? Input / output. So you don't need your bubbles to accommodate them. Okay? All right. Let's do a particular problem. Let's now. So those were some definitions. It's probably the only theory in sequential logic. I will now want to move to a new topic. Again, it's another new application. It's not a new topic. I call it a new application. And we want to show you something called sequence detectors. Sequence detectors. Right? Now, before we move on, if you do not understand my lecture, and the nature of sequence detectors, in fact, even the problem one. So I've given you in our project, there are two problems. Problem one is, problem 1 and 2 both are design problems. The problem is stated, you have to come up with a circuit and make the circuit work on software, all right? Okay. In fact, I wanted to ask the technicians to make you guys do it in hardware, but they said, no, there's no parts, all right? So anyway, both problems, problem 1 in the project and problem 2 in the project is on design, okay. Problem 1 is like what we've been doing up till now, like last week's tutorial. What is it, an even number sequence? Yeah, even number sequence? All right, last week's tutorial. Now, we call those sorts of problems sequence generators. Sequence generators, because your circuit, your end circuit, your final goal is a circuit which generates that sequence, right? Now, the opposite of a sequence generator is sequence detector, right? So that's what we are going to do, sequence detector, right? Now, let us just say, okay, if you, one of your friends missed the lecture, they can come to sequence or pattern detectors and they can watch my video from last year, right? So you'll find my videos from last year all available, right? Okay?
So,
you'll see my videos from last year all available over here. Right? I did it on Microsoft Word, but okay.
And the output is a 0. There we go. So that's how I put it there. Alright, if it's okay with you guys, I will go from when you receive a 1 in C.
Okay, so basically you can find my videos if you want to catch up, alright? Okay, just in case you don't like me, or you don't like my shirt, or you have some problem with me, that's fine. I've made a list of different videos over here from different educators. But remember, the nature of the game, wow, this guy is really educational. The last one. All right? Okay. But don't watch that now. Okay? All right. The thing about these topics is every person has a different approach. But eventually, the circuit, well, the state diagram will come to be the same. Once you have the same state diagram, everything follows in the same sequence. All right? So all of these lectures, the risk over here is you may end up in a scenario where you can confuse yourself because all of these guys have a different approach, right? And even I have a different approach. Right? Family guy has a different approach. Okay? All right. Now, okay. Let's start off with the problem. Okay, so the topic we are on is sequence or pattern detectors. All right? Some people call it sequence detector, some people call it pattern detector. All right? Now, what is it? What is it? So, a pattern detector is this. Right? It detects a fixed combination or pattern of bits in an incoming or given bit stream. All right, let me give you an example. Let me give you an example. Let's say, let us say, example, right? Example, this is the stream of bits. This is the stream of bits. Let me give you a stream of bits. And remember, in sequential logic, one of the most important things for you to do is to be neat. Your neatness is very important. If you confuse the lines, you can mess up a lot of things, all right? Right? And we have to detect 1, 0, 1, 1. So I'll give you an application, something which you can relate to. But of course it's a bigger, this is just 4-bit. Have you guys, most of you have a PIN code, right, for your mobile phone. PIN code or a pattern. You know, you have a pattern to log in. Like forget about, okay, I know some of you guys have fingerprint detector and all that part, fine. But in the old days, if you go one generation, just 2 years or 3 years ago, everybody had a PIN, 4-number PIN or 5-number PIN, right? You have to type the PIN. So if your PIN is, let's say, 9876, right? You have to type the PIN in the correct sequence, then only do you get entry into your phone. Right? Okay, it has to be in the right sequence, right? And so long as you get it wrong, there's no entry given. This is the application. That system, of course, that's based in software. We are going to build it in hardware, right? Well, we build the circuit for that system which is supposed to be built in hardware, all right? So this is the question in this example. The example is we have to detect the secret code, which is 1011, right? Okay, you may be wondering, how is 1011 different from 9876? The only difference is 1011 is a 4-bit detection, to be done, and 9876 is 16-bit code to be detected, right? Because 9 is 4 bits, 8 is 4 bits, 7 is 4, you have to make it 4 bits, 6 is 4 bits. Right? So 4 times 4, 16-bit sequence to be detected in a string of incoming stream. So this sequence is also used, okay, I've given you a very easy example, a security example, but this sequence detectors is also used heavily in something called TCP/IP. TCP/IP is transmission control protocol. This is a particular protocol used over the internet. So you package your file, whether it's a video file, audio file, whatever it is, into packets, and the packets has some kind of addressing code. So your system detects the bit pattern, right? Okay. So basically, there's many applications, but I'm just giving you an easy one which you can visualize very easily. All right. So this is the incoming stream of bits. This is the stream of bits, and our output, we have an output Z, Okay, and this is incoming stream of bits. Let's call this guy X, right? X is our input. Our output, Z, should turn on, should become 1 when the stream is detected, right? The output Z should become 1 when that particular 4-bit string, that 4-bit pattern is detected. So in the first bit, let's consider over here, the first bit, is that detected? No, nothing detected so far, 0. Second bit, there's still not enough bits, right? 0. Third bit, 1, 0, 1. No, nothing detected, right? Because we have to achieve the full pattern. We have to achieve the full pattern, right? The fourth one, no, 1, 0, 1, 0, we now are able to compare. We can now compare and say, hey, is this it? 1, 0, 1, 0. Is that similar to 1, 0, 1, 1? No, answer is no. Now, what do? We move. We move our window for next one. Next one, we move our window to this. That much, right? So we look at our window this much, right? 1, 0, 1, 0, 1. Is that the same as 1, 0, 1, 1? No, all right? Because this one has popped out. We now move to the next one. 1, 0, 1, 0. Okay, sorry. We have to say no to that. Next one. 1, 0, 1, 0. Is that the same as 1, 0, 1, 1? No. Right? You may be saying, but hey, 1, 0, 1, 0 is very, 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 very similar to 1, 0, 1, 1. Right? If you look at this, your 1, 0, 1, 0 is very, very similar to 1, 0, 1, 1. That's like saying your PIN code was 9876 and somebody typed 9875 and they got entry. You have to have a perfect match, right? It has to be a perfect match. Now, let's look at the next one. 0, 1, 0, 1. Is that a match? No. Can you see my window continues to move, right? Now, let's look at this one. 1, 0, 1, 1. Yes. So output is 1 here, right? And depending on the question says it's a repeating sequence, then you can continue going. 0, 1, 1. Answer is no. 0, 1, 1, 0. No. Can you see I'm pasting the particular answer directly underneath? 1, 0, 1, 0. Answer is no, and then we get a shortage of bits, and then the answer will become 0. So obviously in the beginning, in this particular scenario, you do have zeros, right? And the word I want to teach you over here is repeating sequence, right? Repeating sequence. Repeating sequence means that you have a particular bit to be detected, which can be detected twice or 3 times in the incoming bit stream. So if you look at the problem is very simple. Only when you have the exact pattern, then and then only do we say an output is 1. So let's now attempt a problem. And this problem, I'm going to replicate this from the one which I did last year. It's exactly the same problem. It's a very basic problem. So let's look at example number 1. Let's say it says design a milli machine. Design a milli machine. For a circuit which produces output, let's say Z, output Z to equal to 1, when input X has the pattern 1, 0, 0, 1, has received when input X has received the input one pattern 1001. Overlapping sequences are allowed. Oh, by the way, guys, another application of this pattern detectors is in vending machines. Obviously, I'm just showing you a very simple problem, but we'll do later problem because you've got to, this is the fundamental problem, the basic problem number 1, what we call the hello world problem, all right? The entry level problem. Later on, we might have problems where there'll be detect 1001, detect 1011, or detect 1010, triple combination, right? So that's how a vending machine works, right? A digital vending machine would work, okay? All right, now the first thing, so we follow step by step. Again, it's a design process, right? It's a process, which means we follow step by step. Now, it's a milli machine. Milli machine means, does our state have to accommodate the system output? Does the state bubble, in terms of the state diagram, does the bubble have to accommodate the output? No. Milli machine, no. More machine, yes. Right? So let's just do a quick revision. More machine. In our more machine, the bubble has to include the output. So it can be either 0 or 1. Right? Usually more machines are in this thing here, state diagrams for pattern detectors. All right, okay. Now, okay, let's continue, guys. Let's continue. I don't want to hold you up. All right, so the pattern to be detected. The pattern is 1, 0, 0, 1. How many bits, guys? 4 bits. That means 4 stages to be detected. Right? That makes sense. If there's 4 bits to be detected, so that means you can only detect it in 4 stages. Right? You've got to first check bit number 1, then bit number 2, bit number 3, bit number 4. If this 4 is in the right sequence, then only you can say yes, entry is given. Yeah? Okay. Now, if there's 4 stages to be detected, therefore, there should be 4 states in the state diagram, since this is a mealy machine. All right? Okay. Now, let's have a look at the next part. So, until now, everyone with me? Okay, good. Now, the next thing I want to introduce you to is something known as, this is absolutely not necessary, guys. I'm only doing this in the introductory stage, right? Okay, so what is called the working table or analysis table, we call it the analysis or working table, and the bit to be detected is 1, 001. The working table or the analysis table. All right, guys, once again, this table is only for teaching purposes. once you have understood the concept, you can jump directly to the state diagram. Just like everything else I've taught you. I was teaching you how to do divide and find the remainder. I was teaching you how to label the windows of the Carnot map. After a while, once you know the pattern, you don't need to do it anymore. Right? But if it makes you feel comfortable, that's fine. That's fine. You can do it. All right? Okay, so what I'm saying is this is, in some YouTube videos you will find this, some of them you won't. All right. So this table, this is the way I do it. Okay? You have a state. You have something known as receiving input, or some people call this the past input string. String or stream, whichever one you want to use, all right? Current possible inputs. Current input set. Possible next state, or sometimes people says the go-to state, right? And this is the system output. Let's call it, what was our question saying? Say Z, yeah, Z. Receiving input, right? Current possible input, okay? Yes. All right. So this is the table which I have here. Right? This is only to show you step by step how this thing works. All right. Now obviously we always start with state A. We always start with state A. Right? Now receiving input. In state A, when you first start the system, the very first round, we say, okay, this is empty. There's nothing in the buffer. Right? It's empty. The system is empty. Right? In the first state, we say this is the first bit to be processed. Right? Another thing is people say system is blank. Right? I'm just putting some notes down over here. Right? It's not that you have to do this in the exam and all that. Even this whole table is unnecessary. Right? It's unnecessary if you are good at the system. Just like labeling the windows of the Carnot map is unnecessary if you know how to read the Carnot map. Okay? All right. Now, current possible inputs. There's only two possibilities always. You can either have a 0 or you can have a 1. You can either have a 0 or you can have a 1. So let's now look at this, guys. If you have a 0, does that match with the first bit? Yes or no? No, we are looking, what are we looking for, guys? We're looking for a 1. So 0 across, 1 there. So the current input set, right? Current input set is 0, 1. So this is, because it's the first line, so everything will be replicated. The next state, because this was a 0, it can't move forward, right? Because it was a 0, it can't move forward, so we stuck at A. Output is what? It remains a 0 because we haven't found 1001. So when can you say, will this 1001, when will Z become 1? When will Z become 1? After how many bits have been processed? At least 4 bits, right? At least after 4 bits, then only can we have Z equal to 1. and this moves to B, because we have qualified. It's like almost like a knockout soccer tournament or knockout football tournament. You pass one, then only you can move to the next stage, right? So you pass, then we can move to the next stage. But we haven't won the tournament yet. You haven't won the tournament yet. So next stage is B. Now in B, the receiving input, which means past input or previous input stream. So what do? We just bring this here. What was the previous input? In order to qualify for B, right? So it's like from in order to qualify from pole stages to quarter stages, you must have passed the quarter stages. All right? Okay, now, what are the possible inputs, guys? It's either a 0 or a 1. So every stage you will have either a 0 or a 1. So 0 does that get in? So let me just write this over here. If we put these two together, we have 1 0 or 1 1. Right? Now 0, is that the second bit? Yes. 1, is that the second bit? No. So this is no, this is yes. So obviously that qualifies us into the next stage. This one, 1 1. Are we able to use the 1 which is just received? Yes, we can go. If you look at this second bit, if you look at this last bit over here, is that available anywhere in this line? Yes, it was available in B. And this one will be 0. Because why are we putting zeros over here? We still haven't completed the 1 0 0 1. All right, let's move to C. Now in C, what do we fill in over here? What is the past input? Who qualified? Basically, let's look at it from the point of view of a tournament, like a football tournament or something. Who qualified? It was 1 0. So we bring that 1 0 here. Over here, this line over here can only have two possibilities. It can only have a 0 or a 1. Now, if we put these three together, 1 0 and 0, that becomes 1 0 0. This becomes 1 0 1. Now, we look at this. 1 0 0. Is that there? Yes, that's in. What about 1 0 1? No. This one was yes. This one was a no. All right. So obviously, if there's a cross here, there'll be a cross here. So they'll go in parallel. Right. In fact, sometimes if you look at my YouTube videos, I even don't have this column here, but I'm just putting these extra columns to show you. All right. Okay. Now, because this guy qualified, he goes into the next stage. What is the next stage, guys? D. Right? But has he won the tournament? No. He hasn't found 1 0 0 1. What about this one? 1 0 1. Interesting. Now, is that 1 useful in any place? Is that 1 useful in any place? Yes. That 1 is available here, B. Right? We still have a 0 because we can only get a 1 if you have 1 0 0 1. Right? Let's move to the last round. Right? Let's move to the last round. Okay, who qualified from the previous system? It was 1 0 0. Over here, you'll only have two possibilities, 0 and 1. Always. In every state, you have only two possibilities, 0 1, 0 1, 0 1, 0 1. The current possible bit, not inputs, I want to correct that. It's not input. It's current possible input bit, singular. Current input bit, okay? Just one bit. So possibly there's only 0 or 1. This is the input set. Can you see the difference in the word? Single bit. Single, right? Current input set, which means a string, right? And next state is the state, right? Current state, this is current state, this is next state. We can call this current state, right? And output Z, right? Okay, now let's come down here. Now if we put these three together, 1 0 0, and this here becomes 1 0 0 1. 1,000, is that present? Is that present in our thing here? No, it's not. It's not. So we know that's out. What about 1,001? Bingo. It's in. Right? So obviously D is the winner. We put a 1 there because we found the answer. Finally, we have achieved what we wanted. Right? What about this guy here? 0 was the last bit. When was the last time we saw 0, guys? We never saw 0. No, just a plain 0. Is there a plain 0 anywhere in this line over here? Plain 0. We always look at the last bit, eh? The last bit. When you go for into this side here, we look at this last bit. Okay? If it qualifies, if there's a tick, you go to the next. But if it's a cross, you have to look at the last bit. Is there a 0 in any one over here? No. So we go back to the whole system again. A. We go back to the beginning. Start. Back to start. What about 1001? And I think the question, did the question say repeating sequences are allowed? Yeah, question said, yeah, okay, overlapping. Right? So 1001, are we able to recycle this 1 for the next round? Is there a 1 in the system? Yes, there is. There's B. Okay, that's the table. Right? That's the table. And we'll do more tables shortly. Let me show you how to convert that table into a state diagram. Okay, I hope you have that in front of you. Everyone got the table? Has everyone got the table, guys? Yeah? Okay. So before we finish, I want to draw the state diagram. So how many states were there, guys? How many states?